Hey guys, so today we're going to pick up where we left off in class yesterday, and we are going to continue with the Chapter 1 PowerPoint, working our way through some fundamental items, okay? I know we finished this example in class, but I wanted to go over it again, just to kind of refresh. Let's get started. This says, calculate the pressure exerted on the spring's scale, okay? So we're looking for pressure. And it gives us the truck weight. So here's our little truck that I drew. Thank you. It's great. I know. And it is 32,000 pounds. All right. And it is sitting on a scale. We're going to assume that the distribution of weight from the truck on the scale is even. And it is 12 foot by 30 foot. Okay. So we need to find our equation for pressure. Right. So our equation for pressure, as we just went over, is pressure equals force over area, right? So we first need to calculate the area of the scale. So first of all, calculate the area of the scale. It is 30 by 12 foot, okay? 30 foot by 12 foot. If we multiply that out, right, because area equals length times width, okay, 30 times 12, our area is going to be 360 square foot, right? And next, we need to convert square feet to square inches. Now, you can do this by saying 360 square feet equals, you can do this by having 360 square feet and multiplying that by 144 square inches for every 1 square foot, right? Feet cancels out, you're left with inches, and that would give us 51,840 square inches. Or if you want to do it another way, you can convert it before you multiply, right? So 30 feet times 12 is 360 inches, and then if we multiply that by 12 times 12, 144 inches. Alright, we just did that down here. 360 times 144 still comes out to 51,840 square inches, which is the area of this scale. Right? So, to find the pressure being exerted over that, we already know our force is 32,000 pounds. So, all we have to do is plug in our values into our formula. So, the pressure is going to equal our force, 32,000 pounds. Right? Remember that that pressure can be measured in PSI, right? Pounds per square inch, which is what we're going to get here. 32,000 divided by 51,840 square inches, okay, and that is going to give us, divided by 51,840, that is going to give us 0.617 PSI, or pounds per square inch, okay? That means for every little tiny inch of this scale, this spring scale, 0.617 pounds is being exerted on it. All right, we're going to move on. Does air have weight? Now, we calculated basic pressure, right? When you apply pressure to something, apply a force. But we have to realize that the air around us also has weight that it is exerting on us all the time. All right, so during the 1600s, the idea of a vacuum was considered impossible. A vacuum is somewhere where there is no air, right? So can we all agree that there's air all around us all the time? We can? Okay, cool. During the 1600s, Evangelista Torricelli discovered that air, despite being invisible, does in fact have weight. It doesn't weigh nothing, right? Atmospheric pressure is defined as the pressure measured in absolute due to the weight of the air above the point where the pressure reading is taken. This is about 14.7 psi at sea level. So if you are sitting here on the earth, okay, little dude, right? For every square inch of your body, there is 14.7 pounds of air pressing in on every inch of your body. Okay, due to the weight of the atmosphere above us, right? The air and the sky. I don't know exactly how high the atmosphere goes up, but I don't know the exact number, but it's a ways, right? So if you were laying on the ground, okay, down here, you have to realize that there is a column of air above you, right? There, for every inch of your body, there are so many feet of air above you weighing down on that. All right? It's the same thing like when you go underwater, right? If you decide that you want to go underwater, I wish I had a blue pen. Right? You decide to go underwater and you want to sink to the bottom. Okay. Right? As the farther you go down, the more water pressure there is on you, especially on your ears. If you go down far enough, your ears are going to pop, right? Because of the pressure difference. Okay? That is exactly the same thing, but instead of water all around us, we have air all around us all the time. It doesn't weigh quite as much, but it does weigh a good amount because we are, hundreds of feet down from the top of the atmosphere, and it's invisible. Phone going off. There we go. Alright, so, vacuum, just remember that vacuum is below 0 psig. It is measured in inches of mercury. We're going to go over psia versus psig here in a minute, but I want you guys to watch this video on discovering air pressure first. The units are actually metric units, but it is a really good video for kind of getting an idea of air pressure. It explains barometers. All right. If you guys want to pause the video here and go ahead and click on the link in the PowerPoint or just look up this video, you can, but I'm going to go ahead and play it in the video, just for you guys that don't want to do that.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Alright, so, I love the little animations in that video. I love all the little TED Talk stuff, so that's why I decided to play it. 1 second. There we go. Okay, so here we go, right? So that was an explanation of air pressure, right? How we know that there's pressure around us, that the air itself is exerting pressure on us. And also how that changes with altitude, right? So if you're up on Mount Everest, okay, like I said, this is about 14.7 psi at sea level, right? So if you're up on Mount Everest versus down here, think about it. You have this much air on top of you, but on Mount Everest you have this much air on top of you, right? So the pressure is going to be less. That's why water boils faster on top of Mount Everest, which we'll get to in a second when we go over the pressure-temperature relationship. Okay. Alright, so now we're going to go over absolute and gauge pressure. Alright, so, doodly-doo. Absolute pressure is the total pressure measured above absolutely zero, which is total vacuum, right? So if you went into space, okay, you were an astronaut, okay, and there is no pressure being exerted on you at all from the air around you, okay, you're in total vacuum. Gotta give this guy a little helmet so he doesn't die. There you go. All right, zero pressure, and you had a little pressure gauge and measured from there. You had a tire, right? You had a little tire, and you stuck a pressure gauge in it. Okay, that pressure would be from absolute, because if you have that tire, right? If you have that tire, there is air pressing out, yes, right? That's how you measure the pressure, the surface area inside the tire versus the pressure, the force of the air pressing out. But if you're on Earth, you also have pressure from the air coming in, right? So if you're at sea level, 14.7 psi, right? And we know that if you have two forces acting against each other, they're going to cancel out. So if you had, so let me rephrase this, all right? Gauge pressure plus atmospheric pressure is your absolute pressure. Gauge pressure is a pressure range using psi increments with its with 0 point at atmospheric pressure, which is approximately 14.7 psi less than absolute pressure at sea level. Right? So gauge pressure equals absolute pressure minus 14.7, sorry. Right? So a way to visualize this is if you draw two lines, okay? I still draw this on every test I take that I have to do pressure calculations because it helps you visualize it and you can see it easier, okay? Here's some other measurements, right? So for 29.92 inches of mercury and everything, but we'll get to that in a minute, right? The important part is to draw two lines. The bottom one is 0 psia, right? All of this area is in vacuum. The second line is 0 psig, right? That is the pressure at sea level. At sea level, okay? Which is 14.7 psia, right? So if you have 10 psig, okay, so you have this tire, it's a real flat tire, right? Real flat tire, and you are on Earth and you stick a pressure gauge in it, and that gauge reads 10 psig, right? Or 10 psi. It'll just say 10 psi, but know that it's 10 psig. Okay? That means that the total pressure, right, your gauge pressure is going to be 10 psig. But that is after you've already accounted for the air pressing in 14.7. Okay? So if you have the force of the tire pointing out and then the force of the air working against it, 14.7 psi, and your total is 10 psi, right? Right here. Then the actual force of that air inside is actually 24.7 psia. It's just 14.7 of that is being counteracted by the air outside. Okay? We'll do some more calculations with that later. Let's see if I can add like a blank slide real quick. Okay? Just to go over a couple more little examples. Right? So say you have a tire. Okay? And it is and you go to air it up, right? You got a little tire gauge that you brought from the convenience store, the O'Reilly's or whatever. Okay, and you check the pressure on it, and it reads 32 psi, right where it should be. Right? We know that since we're measuring on Earth, right? It's calculating for the air already pushing in. This is psig. Okay. Now, if this tire is at 32 psig, what is that in psia? Okay, we can look at our equation here and see that pressure gauge equals pressure absolute minus 14.7, right? So that means we know that 32 psig equals pressure absolute minus 14.7. We're just going to assume sea level, right? It could be a little more, a little less, but we're assuming that everything's at sea level, okay? We're not cooling on Everest. So all we have to do is switch this equation around, right? So add the 14.7 onto the other side. Okay. 32 plus 14.7. Okay, equals 46.7. Right? So 32 psig, convert that to psia, is 46.7 psia. Okay? We can also do this by drawing the little thing I told you about, right? So we have 0 psia, right? Two lines. The top line is 0 psig. In the middle, we know that we have 14.7 psia. Okay? So if we know that this up here is 32 psig starting from the 0 point, so we go up 32, right, then we know, right, that all of this, if we're measuring from the 0 point of PSIA, that this, not exactly a good example, there we go, that all of this right here is going to be the 32 plus the 14.7 of the air, right? And it would still come out, just like we did over here, we added it, it would come out to 46.7. Easy peasy lemon squeezy. Let's move on. Alright, so now we're going to go over temperature, okay? Temperature and heat are two different things. That's something that you have to know, alright? Heat does not equal temperature, alright? Heat is a measurement of actual amount of energy in an object, alright? Temperature is the measure of the intensity of that heat in an object, okay? And this will make a little bit more sense when we move on with the lesson, but just know that temperature is the measure of the intensity of heat in an object, not the total heat quantity, right? You can remember this by thinking, okay, so by thinking that heat content is relative to size, right? So if you have two jars of water, okay, 2 cylinders of water. One is this big, and one is this big, right? Every molecule of water, okay, inside these is at the same temperature, right? So this one is at 40 degrees, right? Nice cool water. And this one is also at 40 degrees. Which one of these has more heat energy? The big one, right? There's more molecules in there to hold that heat energy. They're both at the same temperature, but this one is obviously bigger. Okay? You're gonna have to put, if you stick it on the stove, right? You stick a fire under it, right? You're gonna have to put more energy into heating this one up to 40 degrees, or your whatever temperature you're trying to heat it up to, than you are gonna have to put into this one. Okay? Because there is a bigger quantity of it, right? So heat doesn't necessarily correlate with temperature, because we know that this bigger one, even though they're at the same temperature, we know that this bigger one over here has more heat energy. But temperature just measures how intense that heat energy is, right? 40 degrees Fahrenheit, 40 degrees Fahrenheit. Okay? And there's some different scales down here that we're going to use. Okay? We have the ones that we are going to use is Rankine and Fahrenheit, but there's also Celsius and Kelvin. Okay? If any of you have taken chemistry class, you know that Celsius is the metric. It's what we use in the U.S. Okay, and here's some scales. You can look over them, and there's different freezing and boiling points. I've kind of compared them, right? So Rankine's is just the absolute version of Fahrenheit, right? So it's used to measure absolute temperature, which we won't mess with too much. We'll get into it later in the lesson. Just know that Rankine is used to measure temperature, Fahrenheit, in absolute. Okay, and you get it by taking the Fahrenheit temperature and adding 459.7, right? So if you want to convert Fahrenheit to Rankines, you would say 212 degrees Fahrenheit plus 459.7 equals degrees Rankine. Okay, to that. I'm not going to actually do out the math right now because I'm lazy, right? Let me undo that, huh? Really gonna be like that. There we go. Alright, so other two things you need to know. You know that water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Right? Easy to remember there. Fahrenheit, a little bit harder, but you guys have been raised around it. You should know it. You should know that water boils at 212 degrees Fahrenheit and freezes at 32 degrees Fahrenheit. Now, not every chemical does this. This is just for water. Okay? Ammonia boils at negative 27 degrees Fahrenheit, I believe. Let me double check that. Kind of had a brain fart. Negative 28. So close. All right, negative 28 degrees Fahrenheit. Sorry, I was one degree off. Okay? So that's a huge difference. That's also why ammonia makes such a good refrigerant, and we'll get to that later. All right, so converting temperature scales, okay? These are the equations you will need to use to convert temperature. Make sure you remember PEMDAS. You guys learned this in Algebra 1, right? Order of operations, parentheses, exponents, multiplication, division, addition, and subtraction, right? So this is the order you have to do things in. Parentheses, so you're not going to add this 5 plus 32, or you're not going to do 5 times degrees Fahrenheit minus 32. You're going to do degrees Fahrenheit minus 32, and then multiply that answer by 5, okay? Easy peasy, lemon squeezy. Let's do a couple little examples here. Okay. Let's say we want to convert, let's do a standard body temperature, right? So like 97 degrees Fahrenheit, right? We want to convert 97 degrees Fahrenheit to degrees Celsius, okay? So let's pull the equation for degrees Celsius. It is degrees Celsius equals 5 times degrees Fahrenheit minus 32 in parentheses over 9. Okay? So we just fill in the equation. So that's going to equal 5 times 97 minus 32 over 9. So we do this part first. 97 minus 32 is 65. 5 times 65 over 9. 65 times 5 is 325 over 9 equals 36.1 repeating ones, okay? 36.1. So 97 degrees Fahrenheit is equal to 36.1 degrees Celsius. Right? All you have to do is fill in the equation. And I'm not saying you guys have to memorize these. I might change my mind on that later, but these are really good to know, and I would definitely advise memorizing them. Let's see. There we go. There we go. Okay, let's try another example. Okay, we'll go the other way. Okay, let's try converting 42 degrees Celsius. Actually, let's do a nice big number, right? So over boil. Let's do no. We'll say 42. 42 degrees Celsius. Convert that to degrees Fahrenheit, right? So the degrees Fahrenheit formula is going to equal 9 times degrees Celsius over 5 plus 32. Okay? So we are going to have that as 9 times times 42, which is our degrees Celsius. I'm trying to switch the pens here. Over 5 plus 32. 9 times 42 is equal to 378 over 5 plus 32. 378 divided by 5 equals 75.6 plus 32 equals 107.6. Right? So when somebody says it's 40 degrees Fahrenheit, and they're talking about Celsius, right? When somebody says it's, okay, if you're from Texas, and you're talking to someone from England, and you say, oh yeah, it's 100 degrees outside, they're going to think you're crazy. Alright? And this is why. Oop, that's not the highlighter. Okay? Same concept. Now we are going to learn about the molecule. Okay? Matter is made up of molecules. We are all made up of molecules. Everything is made up of molecules. Right? These molecules contain energy in them, heat energy. And as heat energy is applied to these molecules, they vibrate. Right? By measuring this vibration, we get temperature. So the intensity, how fast those molecules are moving, okay, that is the intensity of heat energy, and that is where we get temperature. Here's some cute little molecules I drew. Here's a water molecule, okay, with the one oxygen and the 2 hydrogens, and then here's an ammonia molecule with the 1 nitrogen and the 3 hydrogens. Okay, just thought that was cool, right? So as you can see in this little animation I have here, as the temperature, so heat energy is added, okay, which causes these molecules to vibrate and move around more, which causes the temperature to go up. Okay? One second. Alright, here we have an intro to heat. Okay? Heat is a form of energy. We already knew that. We went over that like slide 2 or whatever. Alright? It is measured in BTUs or calories. I was right on the calorie thing. Measured in BTUs or calories. A BTU is 1 British thermal unit, okay? It is the amount of heat required to change the temperature of 1 pound of water by 1 degree Fahrenheit, right? So if you took this, they came up with this, and that's why we use the BTU, right, instead of the calorie, because it makes sense like that, okay? So if we took 1 pound of water, okay, and we applied heat energy to it, okay, however much heat energy we had to apply to raise it from, say, 30 degrees to 31 degrees, that is 1 BTU. 1 BTU of heat. Okay? Heat quantity is the amount of heat energy in 2 objects of the same substance of equal temperature. The amount of heat energy in 2 objects of the same substance of equal temperature will depend on the mass of the object. I went over that with the 2 examples up here. Let's see if we can scroll up. The 2 examples that I made up here somewhere. Either way, temperature is not an absolute indicator of heat quantity, right? So I showed you these. I have these 2 blocks of iron right here, right? This one is bigger than this one. Both of them are at 70 degrees Fahrenheit. They're at the same temperature. But this one right here has more heat energy because it's bigger. It has more space to hold that heat energy. Okay? Also, I drew this, but I have already drawn it down here. Good for me. Okay? So, temperature is not an absolute indicator of heat quantity. That's something you have to know, and I will say it again and again and again. Okay? Next. Okay, so this is where things get interesting. One second. All right. This is where things get interesting, but I'm going to go ahead and give you guys a minute. All right? I'm going to leave it on a little cliffhanger there, and we're going to stop the lesson here today. All right? And we will pick this up later. So, when we get back, we will learn about the difference between sensible heat and latent heat. And you guys have a wonderful day.